Today we are very happy to have Peter to give us his seminar. I think everyone is familiar with him. He is a senior scientist in LBU. Yeah, Peter, please.
Okay, yeah, how can I, why is this not, why is my, good, okay, good. All right, yes, thank you. Okay, well, yeah, thanks. It's an honor to be invited here. Anybody wants to have dinner with the speakers, invited over later, but you're gonna potluck. Anyway, yeah, so I'm going to talk about low X physics from a different angle. And the angle is an upgrade that many of us, for the ALICE experiment that many of us have been working on and talking about for quite a few years. But to set the context, I'm going to spend the first third of the talk not talking about the FoCal, but about forward physics at the LHC and what it tells us about low X physics to kind of set the context. And then I'll talk about the FoCal, the forward calorimeter, and what we think it brings. And describe the device, some of the physics, and kind of put it in a larger context. So that's my goal. Right. So very broadly, and this kind of draws directly from Raju's talk yesterday. This diagram is familiar to everybody. It's to the deep structure of matter as a function of x and q squared. And one goes from dilute matter to dense matter. And eventually, because QCD is non-Abelian, some kind of saturation phenomenon has to occur. That's not really a question. The question is, where does it occur? Can we understand it? Can we observe it experimentally? And that's really this last question is really my business as an experimentalist. So if we have a CGC or some other description, do we have a correct description for the structure of matter? And then in particular, how do we test it experimentally? So before I go into any details, there's some very broad considerations of what that question actually, what's behind that question. What does it mean actually to test it experimentally? Well, it's kind of generic that QCD sort of evolves logarithmically in x and q squared. That's the nature of QCD. And so if you really want to test a description, it's all about evolution. It's a famous plot from here on the F2 evolution of the F2 structure function as a function of x and q squared. Any single point, I don't have it here, but I'm sure you all have it in your mind, any single point in that plot is not in and of itself terribly interesting. It's really the ensemble of points and how QCD describes the evolution with exquisite detail, which is really a masterpiece of 20th century physics and one of the great accomplishments of QCD. So QCD is all about evolution. How do things change? And since things change slowly, one has to, this is just explaining why he's not in my seminar. One has to explore a very broad phase space, and that's key. So I'm already telling you one of my main conclusions: the EIC and the LHC together are stronger than either of them individually. That already leads us in that direction. And second of all, universality. So we have many different tools. We've got deep elastic scatter with a lepton probe. We've got proton-proton collisions. We've got proton-nucleus collisions. We've got many different kinds of tools. We've got neutrino scattering, many different tools. But QCD is a theory of the strong interaction. And if we understand the low X structure of matter, I'm not saying the low X structure of matter as probed by proton projectiles. I'm saying the low X structure of matter, punct. And so what we probe needs to be described in a coherent fashion, no matter what the probe. In other words, the correct theoretical description must self-consistently describe measurements in multiple observables in multiple collision systems. A kind of a deep sort of universality of description. And that leads us to borrow a term from our cosmology colleagues, the multi-messenger program, and that's really my theme, is to combine measurements from even elastic scattering and EP and EEA. Well, HERA is on the books, but upcoming EIC and interactions at EIC, sort of diffractive interactions, and then hadronic interactions in EP and PA collisions at RHIC and LHC. So putting all of these together, I claim, and show some evidence for it, is going to be much stronger in trying to understand the physics of this, the deep structure of matter. Putting these all together is going to be really by far the strongest scientific program. So really complementary. Briefly about the LHC, for those who don't have it committed to memory, these are the 4 major experiments, and what we plotted here is simply the pseudo-rapidity coverage of the 4 experiments, ALS, alpha, CMS, LHCb. LHCb is by construction forward on one side, and the solid boxes are what's currently implemented, so-called Run 2, which ended, the end of the last decade. Run 3 is now underway without any substantial change to the Run 2 coverage. Run 4 is different, and I'll come back to that later. So just bear in mind, so LHCb is very forward. Atlas and CMS, of course, have much broader coverage longitudinally than ALICE. This is the ALICE muon arm, and this is the thing I'm going to focus on in the second half of my talk. But first, okay, so really, I've already kind of given it away. So are these complementary to study Loeck's physics? That's really kind of my question. So in order to, before we get into any experimental details, let's consider the theory landscape. And this is kind of, key. This is the starting point for it all. And so let's compare inelastic EP or EA collisions with forward proton-induced collisions. And some, very, very common observables: interaction cross-section, the common structure functions F2FL, and in the forward PA side, inclusive plan production, direct photons, gamma jet, etc. Common balanced diet, common observables. That turns out very beautifully that the theoretical formulation for calculating both certain processes in EA and certain processes in PA are based on a precisely the same forward scattering amplitude, this TLO here indicated here. So this is a matrix element, characteristic of these processes, and this is an interaction cross-section characteristic of F2FL and so on. So they share a theoretical description in terms of forward scattering amplitudes, and this has a deep history in QCD. Even some of these foundational papers predate QCD. This has a deep origin in field theory.
The electron, it interacts electromagnetically.
No, this is a dipole formalism. So the way you interact, how does the virtual photon interact strongly? It splits into QQ bar pair interacts. So that's the dipole. That's the essence of it. So this is about a well-established formalism, and this is all works. So this is well-established theory. So that's the only dense theory curve slide I'm going to show. But this is really essential. The same forward scattering amplitude is used to describe both. And when we talk to theorists like Raju and his colleagues, they we have full support for that. It's not a question. But it turns out that also in this famous EIC report, those of you who follow EIC know that a few years ago, some of us, well, a couple, last year actually came out, but it was really several years in preparation. It was this fat book on EIC physics and all the physics one will do with the EIC. And there is the section 7.5.4, Loeck's gluons and factorization in EA and PA. It has this nice text here, which is, I think, just sort of puts things nicely and compactly. PA collision serves as a gateway to EIC as far as saturation physics is concerned, play an important complementary role. There are 2 fundamental gluon distributions, Weizsäcker-Williams and dipole, and both kinds of probes probe both sorts of fundamental gluon distributions, and one can write down the theory in a factorized form, which is of course necessary for control theory. And this section even provides a very nice table of different experimental observables and which quadrupolar dipole operators they actually probe. And so there's a nice complementary kind of relationship between the DIS and the PA. And one can, with the PA one, even probes transverse length independent, unpolarized gluon TMD distributions, and that we'll come back to. So that's sort of the sort of theory landscape. And now let's get to some experiment. I'm going to spend some slides on where we are today. So this is LHC Run 2 measurements at Loeck's. Now, if you remember, ALICE doesn't have any coverage forward, and so it doesn't have much to say about Loeck's at the moment. The leading guy here is LHCb, and this is a plot from an LHC paper, or I guess it's some kind of public note from a few years ago. It kind of shows the phase-space coverage of all the LHC detectors focusing on LHCb, and this is as a function of x and q squared. So hardness and interaction goes up here, so low x, low q squared we expect saturation is down in this corner, and in run 2, this is dominated by LHCb. And these cartoons are going to reappear. It's not my work, it's LHCb's work. That is a very nice cartoon, and you can run proton nucleus in the LHC in 2 different fashions. Remember, the LHCb is one-sided. It's one side of the interaction. It can either have the proton going towards LHCb, so what goes into the detector is backscattered off of lead, low X and lead, or you can have the lead beam going towards LHCb, and then you're probing high X in lead. And so watch these cartoons as I go. There's a lot of information here. They also have a fixed target, and I'm going to talk about that. So watch these cartoons because the plots are labeled with the cartoons, and that'll help you keep track of what's what. But LHC is really run in 2 modes. You kind of flip the beams, and you can do both low X and high X in the nucleus. So okay, so getting into some data, and these are all published data. This is CMS forward digest, so going as forward as possible in the CMS detector. And here in CMS, eta greater than 0 is the proton direction, so that's low X and lead. And here I've indicated, so as a function of the eta of the dijet pair, high eta is going to be high X in the, that's going to be, that's going to be low X in the lead. It gets confusing. So this is going to be low X in the lead, high X in the lead, and kind of anti-shattering region here. And there's going to be a lot of models coming through, and I don't want to belabor the models. There's a lot we'll talk on the parameterizations rather of the PDFs. I don't want to get bogged down, but these are sort of common PDFs. This is from some years ago, and I'll come to updates of the latest run 2 data in a few slides. But here are 2 common ones: EPS09 and DSSZ. That's what LHC that CMS having to compare to. What's notable is the difference between these 2 models. So EPS09 contains essentially the gluon EMC effect based on X by 0 measurements, and this DSSZ does not. And so pay attention here to the, so blue is DSSZ, green is EPS. So the data is in red. So the data favor EPS09, and that already tells you that some kind of gluon EMC effect is observable in the data. That seems to be kind of cool. So there's much to say about this, but unless there are questions, I want to move on. I just want to kind of flash the existing existing data and their impact on PDFs. So any questions on this? Let me move on. So here's now a more complete compendium. So this is the CMS forward digests in proton lead and some PDF nuclear PDF parameterizations, and there's a zoom of them here, and you see that the experimental uncertainties are much better than the spread of the models, and so the takeaway is this is significant discrimination of these, at least at the time, whenever this is, 2018, these nuclear PDF parameterization. So this kind of gives you a sense of how the data is driving the understanding of the PDFs. And then more recently, LHCb published some, this is now a famous result from LHCb D0 production in the forward and backward directions. So let me make sure I get this straight. So this is high X in the lead. And you watch these cartoons. This is low X in the lead. So you see a suppression in D0. This is the cross section of D0 production in proton lead relative to PP. So if there were no nuclear effects, this ratio will be at unity. You see a suppression in D0 production for if you're probing low X in lead, and not much of an effect at high X. And you see that the data uncertainties are substantially better than the modeling uncertainties at the time. So these forward D0s really drove the nuclear PDF fits very substantially from that time, kind of mid 2015, 2016. So here is now updated. This is a more recent paper, updated nuclear PDFs with. This is now, the next slide is updated. So this is now comparing pi zeros to these nuclear PDFs, and you see that the pi zeros are at the high X region not agreeing well, low X region agreeing reasonably well. Let me see what observations I made here. This is proton lead, and this is now pi zeros and charge pies, and one gets some sense of the difference between charge hadrons, the difference between charge hadrons and charge pions indicates there's some nuclear kind of flow and radio flow and collective things going on, which kind of muddies the ability of these pi zeros to constrain the PDFs. Again, I'm just giving you a snapshot of what's known.
What's the y-axis?
Sorry, the y-axis. All of these is the ratio of production cross-section proton lead over production cross-section proton. So if you see a suppression, this is at probing low X in lead. You see that somehow the production is suppressed. That indicates some suppression in the gluon density at low X. So kind of watch those things. Yeah. So okay. So here's now the effect of the D0 data on these PDFs. This is prior to waiting with the D0 LCB D0 data. This is afterwards, and you see how the uncertainties come down very substantially. This D0 data had a very substantial impact on the fitting of the nuclear PDFs. So that was a big progress. And here's the latest nuclear PDF from the Finnish group, using several sets of data from LHC Run 2. Forward dijet, the D0s, and CMSW production I didn't talk about. And what to pay attention to here is the reduction in uncertainties going from the gray to the pink, and you see very substantial reduction in uncertainty. So this is the kind of the summary slide of how nuclear PDF parameterizations have improved as a result of LHC Run 2 data. So looks pretty good on the face of it. So that's a very quick tour. Didn't spend any time discussing any details, but this is the take-home message as far as it goes. And now I want to present a twist. So remember that this is the biggest reduction in uncertainties is due to the LHCb very forward D0 production. So how does D0 drive the PDFs? Well, you have gluon goes to CC bar, then with the charm quark goes into a D meson, you measure the D meson, that's a messenger of glue. So that's how one constrains the low X glue from very forward D meson production.
Peter, just
Or is it?
quick question on the top two plot. It seems that the series curve, like at the large eta dijet, it's systematically over higher than the data, like around on the right-hand side, eta around 3. The blue boxes, the blue boxes is like higher than the.
Yeah, but the theory curve isn't only constrained by these data, right? It's it's actually the D0s are probably, well, this is the this is forward. So I don't know what that description is due to, but it's, remember, these are global fits, and this is one data set, so it doesn't have to be. Right, so presumably, I think these digits drive this fit to something. You have to ask the same for the detailed answer. Okay, so the way I went very fast. I'm not sure everybody followed, but the point I wanted to get to, just to reiterate, because the next slide is kind of important to set the context, is these fits are to a large extent, at least at low X, which was what we're interested in. The gluon distributions of low X are very largely driven by the LHCb forward D0 cross-section measurements, which are D0 comes from charm comes from glue. That chain constrains the gluon density, or doesn't. And this is a new consideration, which some of us brought forward very recently. So what is this? So this is now a different kind of measurement. This is from Alice in proton-proton collisions at 13 TeV. And this is now a compendium of fragmentation of charm quarks into a whole zoo of hadronic final states. To the degree that Alice has such capabilities, and you can read what Alice is measuring here. You can actually now measure the branching fraction of charm into each of these hadronic final states. So you measure all final states containing charm, all in quotation marks, but pretty good, containing charm that have, all that have significant yield. So it's something we've missed, but virtually all final states that have significant yield. And then you can determine the branching fraction of the charm quark going into each particular hadron species. So what do we see here? So for D mesons, for lambda C, for et cetera, so the Alice measurements are in the black boxes for proton-proton collisions at 13 TeV and 5 TeV, and they sit here for a number. What's interesting is the branching fractions into d mesons from lepton-induced interactions, E plus E minus at LEP and EP at Hera, sit up here at 0.6. So is the charm fragmentation into d mesons universal? Evidently not.
If the measurements are right.
For the purpose of this talk, the measurements are right. There's a cheap theory comment. You can always say
Let me
that.
make it less, maybe let's make it less cheap. Whether our understanding of the fragmentation, what means actually fragmentation,
Exactly,
P
that's
plus
what I-
minus
that's-
versus fragmentation in PP collisions is the same.
So how
The
do you know?
universality.
So how is that
question?
done? How do you know it's a charm? Or how do you do that? I mean,
You measure these final states. Again, the logic is there's a sorry, there's a comment from, couldn't see that comment from Florian, or
What does he say?
what does he say? I can't see.
If you touch on the screen, you can.
I think you just put it on the chat.
Yeah.
Just look at the chat again.
We'll just tell him to unmute.
Florian, can you say your comment instead of?
I think it's late and he doesn't want to wake this house
Oh,
on.
I see.
Okay, let me read it. Regarding the digest production, regarding digest production, right? And disagreement from theory, most forward data points at the edge of the tech. Okay, this is he's quoting from a CMS paper.
Okay.
Most
Previous point.
yeah, some kind of acceptance thing. Yeah, he says CMS also recognizes that limitation.
Okay, thank you, Lauren.
Anyway, okay, so I mean the charm's got to go somewhere. So if you notice here, this is lambda C, the most common charm baryon. It's inverted, right? So charm's got to go somewhere. So somehow the charm tends in hadronic collisions tends to go more favorably to baryons than mesons. Now, so why do I raise this? Because oops, why is this not working?
Yeah, I have a question.
Let me just make that point. I said, like 5 times, it's enough to be annoying, that, this is largely driven by the d mesons, but that uncertainty in the fragmentation was not taken into account here. That's
Just one fair comment is we've seen similar things for strange quarks as well. But the issue here is that you really produce a hot part on well understood.
so the
Because
two
of the mass scale of the.
two interesting distinct questions is fragmentation universal, and can you use it to constrain PDFs? Remember on the previous slide, we're using the D to constrain the gluon. So now, does this raise a question whether that's a legitimate connection? I think it does.
Is it possible caused by the hard medium effect, QGP effect from dissociation?
And proton-proton collisions? So next slide may help answer. Right. So this is a very pretty study by LHCb very recently, just in the last couple of months. So this answers not precise, but I think it goes some way to answer your question. So this is now the ratio of production cross sections of lambda b now in the beauty sector, not the charm sector. Lambda b over b meson, the ratio of production cross sections. This is just LHCb, and what is this? This is just kind of event multiplicity, event activity, the number of pions produced in the event, the violence of the collision. This so-called velo is there, some scintillator that counts the number of particles produced in the entire collision. Again, proton-proton's a 13 TeV, and it's got some dynamic range to it. And what you see, and this may go in some direction to answer your question, what you see is that this ratio of production cross sections kind of depends on the hadronic environment. If you ask for very violent collisions, you get a high ratio, more baryons produced. If you ask for kind of a minimum bias, you get, or kind of low hadronic activity, you get a low ratio, and the ratio really tends to that observed in ZDKs at LEP. So this kind of goes perhaps in the direction you were hinting, or saying that it's the hadronic environment, the QGP or something else, it's the hadronic environment evidently the hadronic environment is affecting the ratio of heavy flavor into baryons and mesons. And then, sorry?
Could be platonic environment, not quite QGP, but just some color charges around.
Rephrase, the environment of hadronic collisions. Presumably partonic, yes, in nature. So none of that has been taken into account here. So that's kind of where it
There's
was.
a question online.
Yeah. That's online. Suraj, yes.
Yes, sir.
Hi, Peter. So, more than hadronic, this could be related to the multi-parton interactions and how the color flow happens between these multi-parton interactions. So, how do these, so if you are using PA to constrain the PDFs, how can you take this into account if you have multi-parton interactions? This is not like a simple
excellent.
scattering of a quark or a gluon, right?
Excellent question. Clearly it requires modeling. I mean, one could certainly make some progress there. But to be blunt, I don't have to answer your question, and I would, say it, differently. How reliable, how constraining really are, hadronic measurements for constraining low X physics, given this uncertainty? Given the need to model multi-partonic interactions, one maybe come up with experimental tricks that can limit that. This perhaps, this guy perhaps hints, you may ask for very little hadronic activity, but then how you're biasing in terms of impact parameter. I mean, it's just a mess.
There's an uncertainty because of that fact.
There's uncertainty,
To
but how do you,
be taken into account in fits.
right, it has not, just to repeat, I'm gonna repeat myself ad nauseum here, has not been accounted for. That's something that absolutely has to be borne in mind. And this I only realized in the last year. Okay, so that's, I could spend much too long on my introduction, but I kind of set up the question. So how to do it differently? Answer in one word: photons. Don't measure hadrons, measure photons. So how are you going to do that? And that's what I'll spend the rest of the time at. So that's kind of the stuff. Summary, the first part is one word: photons. Okay, so this is the FoCal, and I'm going to spend a little time defining it, and then I'll kind of show what it does. So this is an upgrade planned for installation in long shutdown 3, and for those of you who don't know when that is, we would start taking data in LHC run 4, start at the end of the decade, 2029. And main physics goal is low X physics. This is not the scale, this is the Alice device, here's the muon arm, this is a central detector. It would be on the open side, not covered by the muon arm, and there's open phase space there, and it's got shows you what kind of engineering you do to support this thing. It weighs several tons, is a calorimeter. And here's a pseudo rapidity coverage going very far forward, out to eta of 5.8. I'll say more about its coverage in a moment. And the flagship measurement is isolated direct photons down to very low PT and very forward eta, going to very low X. And the number to bear in mind is 10 to the minus 6. That's a low number. That's a very low number. Even 10 to the minus 7 in proton collisions at 13 TeV, but it has quite an array of capabilities. So inclusive, pi zeros and other neutrons, isolated direct photons, jets of peripheral collisions. Spencer is the one to tell you about that. Vector bosons and correlations of all of the above. So to come back to this plot, this is in kind of crude terms, this is what it would cover. So now complementary and going forward to LHCb, and I will show more detail of that in another in a moment. Now, given I spent so much time on the introduction, I'm not going to spend any time on this except to very briefly so the kind of soul of it, the key is the electromagnetic pieces. Electromagnetic plus hadronic calorimeter. Hadronic is fairly conventional. It's copper tubes with scintillating fibers and fairly conventional design. The FoCal E is what makes the whole thing go, and it's silicon tungsten. With about 20 layers, so there's the absorber, tungsten absorber, and then the sensors, and there are two layers, 5 and 10, are ultra high granular pixels, tiny pixels with pitch. I've got it on here, yeah. So 30 microns on a side. So you image the shower in exquisite detail at a couple of places, and that allows you to discriminate pi zero decays into 2 photons from a single photon, which is what's needed to do direct photon measurements. And the discrimination is really extremely precise. So it's a kind of on the way to tracking calorimeters, which have been developed for generations for the ILC and so on. This is one of the first silicon-based calorimeters that will be put in condition.
You really see the 2 photons of the pi zero.
This is a simulation. We've got test beam. This is a simulation. So this is. Look at the kinematics. 8 of 5, PT of 10. You see the 2 of them. You see the 2 photons. It's extraordinary. Okay, so a lot of documentation.
Why is it?
Huh?
Because you have a rapidity of 5, I mean, these two photons go together like crazy, right? And
But
we
no,
can make
you're 7 meters down the beam pipe, you have millimeter separation.
exactly.
If you put the
Yes.
detector far and it's highly granular.
Yeah.
Microns, the things are microns, so we've thought it through.
I declare myself impressed
Okay, good.
until I see the real data.
Okay, right. We have real data,
Okay.
testing, okay? Right, so here's now
Do we
the,
have unreal data? No.
here's x and q squared for the FoCal in the context of LHCb, so we see we're now going down to 10 to the minus 6. This is for electromagnetic probes, including photons, and for LHCb, Drell-Yan, and this is for hadronic measurements, pi zeros, et cetera. So you see the coverage is now going really quite low. This is for PA collisions, and again, to repeat, for proton collisions is 14 TeV, we go below 10 to the minus 6. So unexplored phase space by a large factor. EIC, to remind you, is up here at 10 to the minus 3. So again, remember my first slide, logarithmically large phase space. This is what we mean. Okay, so very briefly, and when Qingwei, we had this plot is answering a question we asked in a group meeting a couple of weeks ago. Okay, so what does it mean to be super forward? This is just simple, textbook kinematics. If we have a transverse momentum of 10 GeV and a rapidity of 4.5 that is in green, you have a longitudinal energy of 500 GeV. It is tremendous energy because it's so forward. And that means you have to think about calorimetry in a completely different way. It's not at all like calorimetry in the central barrel. Okay, so it's just different world. So that that tells you, you can do things that perhaps you can't in the central region. There are other complications regarding jets, which I'll get to in a moment. So that answers. Okay, so here's some projections of luminosity. Those are just numbers. This plot, what is this plot? This just tells you, so what, to build this thing and put it there, does QCD provide a rate? It does. And what is this? This is cumulative counts for some of these luminosity projections for different observables above some threshold. So for instance, for direct photons in proton lead, above 40 GeV, we'll have a few times, a few tens of thousands of counts in a typical run. It's a very, very healthy slug of data to do physics. So you can, from this, you can tell kind of the kinematic reach of this thing. Saturation is way down here. We actually didn't plot. This is kind of arbitrary cutoff. It just, the cross section keeps on going. Our point was more the high end. So saturation is way down here. So also you want to see how things evolve from the saturated region, the unsaturated region. We have plenty of data. So that's really what the takeaway from this plot. Cross sections are enormous. It's the LHC. Okay, right, so the interest of, getting to physics. So FoCal, this is kind of the key. This is direct photon performance. So to do direct photons, you do photon particle identification by various means. In varying mass, you take the 2 photons and you see that it doesn't look like a pi zero. Shower shape, you don't want, for merged guys, you don't want it to be kind of elongated, and they do some kind of isolation. And if we put it all together, we get a very nice performance. We're able to get an enhancement using all of these tools of all electromagnetic, you take a population of all electromagnetic showers, you apply all of these cuts, you ask what's remaining, what fraction is direct photons, is well over 50%. So that's a pretty good purity by the standards of the way one does in direct photon measurements. That's good, and the pi zero efficiency is also understood. You need the pi zero efficiency to be able to correct. And so these are kind of technical plots, but this all hangs together for a very robust, precise measurement. So I'm hurrying. Florian is really the expert on this. I'm hurrying because I want to get to the physics. Here's now, and I'm going to spend a moment on this. This is now the kinematic coverage. And so for a couple of key channels. So we just measure inclusive direct photons. What does that mean in terms of X? So this is just simple 2 to 2 kinematics calculated by Pythia for proton collisions at 8 TeV, which is the typical energy for proton lead. And this is the X coverage. So if we fix the eta, so we take the whole FoCal acceptance, we look as a function of PT. Low PT photons are down backwards at 10 to the minus 5. Highish PT photons go to 10 to the minus 4, 10 to the minus 3. If on the other hand, we fix PT, we look as a function of eta within the FoCal, we can likewise, tune the kinematic reach. This is logarithmic, so we're going orders of magnitude. So again, logarithmically large variation in exploring phase space. This is enabled here. And now Alice has a central barrel, so we ask for the photon here and a jet in the central barrel, we're covering kinematics. So we ask for a coincidence measure. We're covering kinematics around 10 to the -3, which is EIC kinematics. So by judicious selection of phase space and observable, you can tune the kinematics over 3 or maybe 4 orders of magnitude, including overlap with EIC. So it has really quite a, even though it's a small device, it has quite a robust kinematic
Sorry,
coverage.
what's the X range in the top plot?
Sorry, this goes, can't read it, 10 to the -6 to 10 to the -2.
Okay.
Sorry, yeah, this is all, are they all the same? Not exactly, pretty much. So this is all, the left, sorry, yeah, too small, I realize. The left side is always 10 to the -6, and then you can see 1 decade. So that gives you, so 1, 2, 3, 4 decades. So that gives you a sense of it. So EIC kind of covers this region, and we go backwards. Again, this is logarithmically large kinematic coverage. So if you do those photon measurements, and this was a study that was done by Florian, let's try to see what pseudo data from the FoCal would actually do for constraining the PDFs. And this is now a reweighting of a standard high order PDF for protoproton collisions using first of all D0 data, and that is, sorry, the colors kind of overlap. So the gray is this version of PDFs with there's nuclear PDFs, but high order next the leading order, I guess. So the gray is without incorporating the D0s. Incorporate the D0s, you get the blue. If you don't incorporate the D0s and you incorporate the FoCal, you get uncertainties that are comparable in magnitude to the constraints provided by the D0s. So you would say, okay, why bother? You're not doing better. But I come back to the question of uncertainty in using hadronic observables to track the gluon density. So this is now using a photon, which does not have the fragmentation uncertainties, to do the same thing, and using projected pseudo data with statistics appropriate to the integrated luminosity, we get just about the same constraints. Okay? With systematically very different. Now the real answer is, I'm not telling LHCb not to measure. If it's interesting, and surely LOX is interesting, you want to do it multiple ways. And again, test the universality. And maybe one can even learn something about the
So what's the X value for this plot?
This is all kind of convoluted. This is R, yeah, sorry, the slides are too quick. This is again RP LED, so the ratio of production cross sections for photons as a function of PT. So again, nuclear effects suppress the ratio below unity. So it's a ratio.
That's over the total rapidity coverage of your.
That's right.
FoCal.
That's right. So the suppression below unity is nuclear effects on the PDF. The blue would be due to LHCb current data, and the red would be due to the photons. Similar magnitude of reduction in uncertainties, but with very different systematics.
So what luminosity is this for, Peter?
Oh, this Florence should answer, but this is I'm certain it's close to what I show in red here.
Let him speak. You just want to say.
Yeah, it's very close to the it's the one shown in red here. So that was for PLED 100 inverse nanobar.
Okay, so this is projected from run 4 or like
yes, exactly. This is the projection for run 4. Yeah.
Okay. Well, you said 100, but I have 300 written here. Did you mean 300?
Yes, I think. Yeah, I think I actually used the 300. This I have to double check. The actual number is 300, but in the cumulative yields we were more conservative and used 100. Yeah.
Right. So just for this plot, we use 100 here. I mean, these numbers in the upper left box, they're going to change. I mean, run 4 is years away. These are all going to change. If you do a rate plot, it's just qualitative. Do we have rate above something? You want just round numbers. So we chose 100, and then you can, if you would like 300, you can just multiply the rate by 3. So that plot is for convenience. It's not precision. These are closer to current run 4 planning, but that's going to change as years go by. So, okay, good.
I have a question on the RPA. So what is the main systematic uncertainty on this FoCal pseudo data for this boxes uncertainty?
That is for Florian's answer.
Yes, I can answer this. So the uncertainty rises at low PT. This is mainly driven by the purity extraction.
Okay.
And so it's essentially an artifact from the fact that your signal to background ratio gets lower at low PT. And we estimated this using sort of two different ways. One was estimating a certain uncertainty for pi0 reconstruction and photon reconstruction, and then propagating it with the signal to background ratio from NLO to achieve, these uncertainty boxes. And another way that gives equivalent results is you sort of translate the systematic uncertainty that you had in run 2 measurements as a function of the purity. You translate it to the purities you observe in simulations of the FoCal data, and then get the same box.
Thank you.
Okay, let's go on to another topic, jets. I like jets. Jets are very hard in the forward direction. But why are they hard? They're hard because phase space shuts down, and this actually illustrates how that works. So first of all, jets are super interesting from the point of view of measuring saturation, in particular dijets, balanced forward dijets, and you want to measure the kind of the imbalance between them, which it's actually the imbalance between them which probes the saturation scale. So that's the golden measurement as far as jets go. So let's see whether we can actually measure jets. Jets, to remind you, are they're remnants of a virtual quark or gluon created in the collision, which sheds its virtuality by a gluon shower, which eventually turns into a spray of ions and whatever that you see in your detector that has a width. So, and that width is what's tricky. So this is now it's not even a jet, it's a hadron, it's one hadron, which I think illustrates the problem here. So what we did a little exercise, a little simulation exercise. We took a charged pion, which will shower hadronically. It doesn't shower in the electromagnetic part of the calorimeter, the hadronic part of the calorimeter. We took a single pion and shot it at some point in the calorimeter. So this open box here in the middle is where the beam pipe goes through. This is just physical space on the calorimeter, X and Y. Looking physically at the front of the calorimeter, we shot it a little bit to the left of the beam spot, so 8.9. This is walking a bit to the right, 4.5, 4.0. This is walking to the right. So a single charge pion here, and then we repeated it 10,000 times. We simulate the shower in the calorimeter, we do it 10,000 times. So this blue distribution is over 10,000 pions, the average hadronic shower in the calorimeter. This red circle contains about 81% of the hadronic shower from a single pion. I'm not even talking about the width of a jet. Single pion is how the physical calorimetric detector responds. This red guy, it's the interaction length of copper, which is the absorber, and contains about 81% of the shower. You think you want to measure a jet, you better, you're not going to capture 100%, but if you capture less than 80%, probably not very good. So that tells you kind of the minimum you need to be able to do in order to capture a jet consisting just of a single pion, never mind the QCD effect of broadening the jet cone. So what's the black guy? The black guy now is what a contour in XY space looks like for a jet of radius 0.6 in eta phi. So a jet cone in kind of momentum space. And that's a fairly healthy cone. That's kind of a large cone that one likes to measure. That's what it looks like here. It's much smaller than the hadronic shower because phase space is so very contracted in the forward direction. It's, you would say, well, this may be impossible to do. So we're capturing, I'll show you in a moment, we're capturing only a limited fraction of the jet energy, and that's true, though we can't make it precisely. So that's really the challenge. As we go backwards, it kind of gets better, and a jet of radius 0.6 kind of more or less captures the fine shower. Now we have to throw real jets at it with some spread, and it's going to get a little worse again. But this looks like you might be able to do something with it. This, not so much. So that, I think, explains why the instrument response itself is what limits the ability to do jets in the forward direction. So when we are stubborn,
How do I understand the unit? Right? So
sorry?
how do I understand unit?
The units, it's just the proportional to the energy in the shower, the density of energy in the shower. So we shoot a pion at this point, and it interacts with the detector, and then it kind of in a you know how a calorimeter works? You have a particle coming in, it interacts, with, strong interaction, and then, sends out, pions, kaons, protons, lambdas, and kind of the whole thing sort of turns into a shower in the calorimeter. The jet shower, which is QCD, this is a physical shower in the calorimeter, and it has some width to it. That's how calorimeters work. It measures energy by stopping, and you stop by putting, absorbers and sensors. The absorbers cause the particles to interact, and the sensors measure the shower. So it's kind of layers upon layers. I showed that in the previous. And so you measure you may measure the longitudinal, but certainly you can measure the transverse distribution of energy in the shower. And so this is so the colors are now proportional to the density. So the highest energy is in the direction of the highest energy density is in the direction of the pion, but there's a long tail, large tail. It's more or less symmetric.
Well, my question here is, how did you decide the Z location and the size of FoCal?
It is as big as we can make it within other constraints. So getting there's a limit to how close you can come to the beam. And likewise, the external size is limited. Maybe Mateus knows more. The external size is also limited by other parts of
There's
LHC.
there's few operating magnets. I think quadruple correcting magnet that does not allow us to go more forward.
Well, that's how far from the intersection. So
On top of
7
this,
meters, 7 meters as far as we can go away from the interaction.
Yeah. And you don't necessarily want to go too forward because then your device is larger to capture some more.
But it's a meter on the side that's covering 2 units of eta, so it's already quite.
And then of course all these doors close at some point, so you have also distance from the interaction points. It's real estate there.
Yeah, it's as big as one can make it within.
Not
just physical
optimization. Yeah.
Okay, so this is now a measure of how well we're doing with the jets. So this is real jets, and looking at the jet energy scale. So some detail of the jet finding, those who know, you can see, I won't go into detail. So this is just a kind of a relative, scale of how well you're doing. So you have it, the energy of the jet you threw at the calorimeter, you measure what's, you report what's measured, and this is kind of the deficit relative to the truth. And you see that, as a function of jet energy, is now total energy is not PT, so total energy of the jet, you see that we're not doing great. We're missing, between 25 and 30% of the jet energy as we go up. So it's not zero, but not great. It's kind of hard to start that way. So we do have some tools to mitigate. And what I showed you that kind of this blue kind of circle in this thing in the last 2 slides ago was the hadronic shower. Remember, the calorimeter has 2 pieces, electromagnetic and hadronic. And hadronic is a conventional, electromagnetic has a super high fine granularity. So can we use that? And now the question is, can we choose our jet? We're interested in dijets and the PT balance between them. We don't care particularly how the jets fragment. Can we come up with a biased population that will give us a more precise result? And can we, in particular, bias our jets towards the jet population that decays primarily into pi zeros? In other words, electromagnetically, so it's measured in the electromagnetic part of the FoCal, we can measure it more precisely. If we want to apply a fragmentation bias on the jets, so it's an observable. If you have both electromagnetic and hadronic, you have a jet coming in. You measure the total energy of the sum of the two, and you also have another observable. You have the relative. You have the energy that's the hadronic piece and the energy that's the electromagnetic piece. These are jet observables. So let's ask for the subset of jets that have anomalously high fraction in the electromagnetic part. This is just a distributed. Well, it's been measured and modeled fairly well, and in Monte Carlo, this is a distribution of the so-called neutral energy fraction probability. It goes from 0 to unity. It peaks at around 1/3, as you would expect, just from isospin. It's very broad, and so this is an observable. We measure both pieces of the jet in the calorimeter, but we can let's just ask a simple question. The hadronic calorimeter that its energy be small. We don't need to know with precision. We just ask that it be small. In other words, trigger on neutral energy fraction being large, And because the electromagnetic calorimeter has so much better spatial resolution, perhaps the showers are smaller and we can overall improve the jet measurement. That's indeed the case. So if we trigger on large neutral energy fraction, in fact, the jet energy scale, remember, large negative numbers here are bad. Zero would be perfect. It goes up to some degree. So we have some tools to try to improve the jet measurement, but this is very much a work in progress.
Now, what's that red versus the black there?
Oh, I'm sorry. Right, so fill is the highest NEF, open is the lowest NEF. This is detector versus particle level. So the red is full detector simulations. The black is just what comes out of the Monte Carlo generator. Okay, so you see the detector effects here, and for whatever reason, detector effects, make it better, but we'll take it. So this is just to give you a sense of what this device may be capable of. 20% is still not terrific, but it's certainly better than 30%. So very much work in progress.
Another nice question. So what level of PID information you have?
Sorry?
What level of PID information you
have? For neutral decays by zeros, we can identify them. There's no tracking. There's no magnet, no tracking. So, well, for instance, I mean, if it, J psi go to electrons, very good. Z go to electrons, upsilon, but it's got to be, into electromagnetic final states. Hadronic calorimeter is probably, it's used for photon isolation, but for particle identification, that's why they they're really responsive. But to my knowledge, the hadronic calorimeter won't do much. This is all based on the very high precision electromagnetic calorimeter. There's no tracking, no field, because it's so very forward that you need a strong dipole, and that's a real mess of collider. Okay, how am I doing on time? Yeah, I'm gonna, this is now, so that's so much for the FoCal. These are theory, just I assembled a bunch of theory calculations that are in the literature. Let me just focus on this, and I'll skip the last point I want to make. Right, so there's a bunch of calculations, largely in leading order, and one has to go to next to leading order in photon production, in coincidence channels, and so on. And this is very much work in progress. I mean, we talked to Raju about this, Finnish groups, and so on. So these are kind of over the last 5 or 10 years, these very forward kinematics have gotten the attention of theorists, and people started calculating things. And so what is this? Again, sorry that I assume everyone's familiar, but I realize this is a mixed audience. So again, this is the ratio of production yield in proton-lead collisions over proton-proton. No nuclear effects, the ratio of the unity. See a plot looks like that, assume that's what it is. So this is now a leading order CGC calculation of suppression due to CGC effects for inclusive pi zeros and inclusive isolated photons. And FoCal will measure these. Actually, as will LHCb in a different way, different kinematics, but likewise, non-trivial measurements. And so I tried, the plots aren't, I tried to align them. So that's 0.6, 0.1, 0.6. Right, so these are aligned. The horizontal axis 2, 10, 1, 8. So not horizontal axes aren't identical, but good enough. And what you see actually is the turnoff of saturation effects for pi zeros occurs over the range of up to 5 GeV and PT, much more rapidly than for photons. Interesting difference, and that's that's in the calculation. These are not the same production mechanism. You want to produce an isolated photon. The color flow of kind of what happens when you come in with 2 hadrons, you produce a photon, versus pi zero is going to be a remnant of a jet. The color flow is different. So evidently, and this is in the guts of the calculation, evidently, the photon probe is sensitive to color glass effects up to higher PT. Now, this paper comes with a lot of caveats, the first of which is they have to now extend this to next to leading order. But nevertheless, this is, I just take this as a, let me put on my naive experimentalist hat and say, well, this is an opportunity. If we're looking at observables that are sensitive to saturation, but are sensitive to saturation in different ways because kind of the color flow to produce them is different, well, then let's do that measurement and to the degree possible in identical fashion to compare inclusive pi zeros to inclusive photons. There's already kind of an A/B, sort of test you might want to do with FoCal data. This already drives us in certain directions of things we want to do.
But does the pi zero have the same problem as your D zero? that you fragment all kinds of stuff and it's not really fragmented. It could be the other garbage which contributes.
You would have to tell me.
Yeah, but I mean,
Hey, look, nature gives us things we can measure and things we cannot measure. So as long as we have the photons, you know, if I were only advocating hadrons, you know, your question would be
but
the
it's
problem.
very difficult to make a story out of the difference between the two, unless you understand this other stuff, right?
Yeah.
This fragmentation difference, as we want to call it.
Sure. Okay.
Yes.
My talk has been, if that message got through, my talk has been a success. Absolutely. So, but you know, we will have pi zeros, we will measure pi zeros, we will report pi zeros, and then what does this difference do to? So that's as much your problem as my problem.
No.
Okay. Yeah, sorry? Yeah. Okay, right, so there's, you know, forward digets being there's a Krakow. This actually, let me just point out, so forward digets, looking, you know, actually at the kind of the angle between the dijet pairs, that's what delta phi is here. It hasn't got a lot of features for, you know, comparing proton, lead. What's notable, this actually is a very nice framework. It's next leading order, and they actually add non-perturbative effects, including jet showering and hadronization effects, in a very nice controlled way. And what I want to point your attention to actually is the theory uncertainty in the blue band on this distribution, which, you know, they brought these effects in and assess the uncertainties, and the theory uncertainties are fleetingly small. Well, this stand up to scrutiny. Of course, we have a few years to figure that out, but I think this is sort of a nice, you know, a nice example of theorists, you know, taking the, you know, the theory uncertainties to compare really to data seriously, trying to make some assessment of what those uncertainties are. And their first answer, at least, is it looks pretty good. So one can imagine, if, you know, this persists to the end, one can imagine doing quite precise comparison of theory and data if these are indeed the theory uncertainties. So I'm going to skip all of these UPCs and invite Spencer to talk about that. There's a whole, I'm going to really flash FoCal performance, because that's not what of this audience is well, you know, is here for. But I want to end with a few remarks, kind of taking a big step back from the FoCal and asking again, kind of in the spirit of my opening slides, you know, what's the big plan? What's the big picture? Let's fast forward 10 years. Lots of beautiful new data on, you know, EIC is running gangbusters. Beautiful data on EP and EA from EIC, and PA from forward RHIC and forward LHC. Tremendous amounts of data. What do we do then? Very heterogeneous data. Very, you know, I talked about universality in different systems and so on. But what really is the plan? How do we put this all together to fully exploit the data and really make, to the degree possible, definitive statements about the Lorentz structure of matter? Do we see, you know, saturation effects? First of all, is CGC the right description? How do we really, you know, get quantitative with all of these? Now, there's a very cute study by Nestor Mesto and collaborators. So I'm going to go very quickly and take a couple of minutes to describe this, because it's really informative. It's a toy model, so don't take it for beyond what it is. But they asked the following question: leave PA aside, just look at DIS data, and just, you know, F2 and FL. Classic standard DIS measurements. And they have a toy model, and they calculate with EIC and LHEC. So this is something I didn't talk about. There's an idea of making EP collider at the LHC, and Nestler is one of the advocates. So that's kind of why this is here. But let's just focus on the EIC component. They calculate, they generate some pseudo data to calculate F2 and FL at the generator level. No detector effects, no experimental uncertainties. And they consider two evolution frameworks, one collinear factorization and the other nonlinear CGC evolution. So you kind of, you generate a distribution at some point in phase space, and then you evolve it in two different ways. And you evolve away from the matching region, and you compare. You say, how different would my measurements of F2 be or FL be if evolution were linear or nonlinear? Right? Interesting question. And here's now the relative difference of so I think the linear difference, the relative difference of nonlinear and linear evolution. So this guy here, the black dash is, so 0, so it's a bit faint here, 0 is here. The black dash is for EIC kinematics 10 to the minus 3. And you see for F2, if you match in some region, which is, should be well linear, then you evolve into the into the saturation regime, you see that the differences are at best a few percent. So that's in a sense a prediction of the magnitude of effect that would discriminate linear from nonlinear evolution for EIC kinematics. FL is a bit better, of the order of 10%. So not zero, but very challenging to measure discriminating differences of a few percent. So that's already DIS from this toy study, and I don't want to make too much of it. Now it raises the question: what is one really going to do with DIS to make a definitive statement in EIC kinematics about saturation? So what's the alternative? And so the conclusion of the first part of my talk was photons. The conclusion of my second part of my talk is Bayesian inference. So very simple. So we have again, let's imagine the totality of data from EIC and LHC and forward RHIC. Vast arrays of data, not all of which map naturally onto their PDFs. These angular decorrelations, acoplanarities are not naturally connected to nuclear PDFs, to collinear PDFs, right? Clearly not. Jet substructure is very interesting, since that the saturation effects energy correlators of deep interest. The people in this building will also be measured and are sensitive to saturation effects, and don't obviously map onto nuclear PDFs. So I think we need to step back and ask, what is the more general way to bring all of these things together to confront complex calculations and complex, very heterogeneous data in a rigorous fashion. And this is an example from another part of my life is Jetscape collaboration, where that's been done for heavy ion collisions. We take two different models and you confront to the same set of data, and we try to predict what the measurements would look like. And this is kind of the deviation of the model from the model prediction from the data, and 0, would be a perfect model. You see some blobs and some things are a little displaced. The two models are not the same, so the details are unimportant here. Sorry, they're both long, but this is just a cartoon of, I think, what one would want to do with saturation sensitive data in the broadest sense from EIC and LHC and forward RHIC to really do this kind of multi-messenger physics over vast space. And with that, I will stop.
If I can ask one more question related to your previous slides. So you said not all those observables map directly into PDF. That means you want to do a global analysis. It really just depends on the observable you choose to fit, right?
Sure. I mean, you can take a subset to constrain collinear PDFs. That's a good thing to do. People will do that, but it's not the entire picture, and does not, I think, fully exploit all the data sets of saturation. That's kind of the point. It's a subset of the data.
So I mean, so what is your proposed observable in this case?
Take them all. I mean, this is
Okay.
so yeah. So for instance, I mean, I went too quick, but for instance, some digits. Dijet KT. So this is within. So it's not a well formulated proposal. It needs clearly very much work and discussion. So this is the KT. It's a Monte Carlo. It's based on next linear order analytic calculation, but with some reality effects for jet showering and hadronization. So a very nice playing ground, I would say. So as an example, let's ask whether the KT, it's called KT, kind of cute name, but it's KT. Let's ask whether it's consistent with the totality of observables. So I would use it as theoretically appropriate to calculate DIS data, to calculate this dijet KT, to calculate direct photon production, and etc. And then in an agnostic, comprehensive fashion, turn the crank on the Bayesian inference and say, is it consistent? Then you systematically remove measurements. You say, do my posterior distributions change? To what degree is there tension? So I think the Bayesian framework allows one to do that in a very systematic way.
So in this case, your Jetscape is basically just a framework to check this particular observable.
Well, I didn't say Jetscape. But just give it two things, just give the model and a Bayesian analysis framework.
Yeah, because
Yeah.
I'm just trying to distinguish between this and the, for example, global QCD analysis. You put like your D0 data or structure function data, all things into that.
How would you work in digit equiplanarity?
But I mean, so it sounds like this case is just like you, for each of the cases, you just handle one observable.
Yeah, so I mean, equiplanarity is not naturally collinear, it's not collinear by definition, right? So you have to generalize, maybe it's, you have to do TMD fits perhaps. But doing it observable by observable is to me unsatisfactory. I think one wants to confront the totality of the data in a comprehensive fashion. Because what if it fits here and doesn't fit there? What have you learned? How do you know where the sensitivities are? If I change, this fit, what does it do for my other guy?
Right. But isn't that what these global structure functions fits are doing?
For collinear PDF. So if your observables are inclusive production is sensitive to collinear structure by definition. You have you suppress your X, you get 0 photos. Clear. Inclusive production, fine. Anything beyond inclusive production, you got to think. So what degree a coincidence, a gamma jet coincidence ring? In what sense is that sensitive to your collinear PDFs and suppression? Indirectly, at best, right? So if it's only indirectly sensitive, then the constraints it applies are only indirect.
Yes.
But is saturation only suppressing the collinear PDFs, or does it have other dynamical effects? And how do we actually bring those together?
I have a maybe more generic principle problem. I mean, you can do a fit and you fit something, right? But if you do Bayesian inference, you might actually know what to change in particular model implementation to improve part of physics that is sensitivity to this part in that model versus the other model. It's more differential analysis.
There are frequent ways to do it too. I'm not saying Bayesian is magic. I'm just pointing out that fitting collinear PDFs is a very limited game.
Yeah, absolutely.
And the data are vastly more expressive than that. That's the only real point I'm making. How you do it is we can discuss.
I think just maybe a closer connection to the type of PDF analysis you're talking about. You can of course start with the global PDF analysis, and you can add whatever modeling is needed to get TMDs and dijets and all of these, but the typical approach is you're fitting the PDFs, and anything else you put in terms of this other physics is kind of assumed to be understood. Right? You kind of factorizing that you can fit the PDFs, well, you know everything else, or you can know the PDF and fit that. So this is,
but that's what
so you could take a fit and make every parameter of every piece of the fit part of the fit, and then you'd be doing something similar to this, but of course you wouldn't have all the advantages that you get from the Bayesian inference. And
right.
It would not have that nice systematic toolkit of it.
Point. Is that out?
Any more questions? Thank you, Target.